In this video, we will learn how to find the time period of a simple harmonic oscillator. In a simple harmonic oscillator, we know that the restoring force over a body is proportional to the displacement from the mean position. So we write F restoring proportional to displacement from mean. The negative sign indicates that the restoring force is opposite to the displacement. Now if I write force is equal to mass into acceleration, and we replace the proportionality sign by equality, then we ought to have a constant of proportionality k times x. X is the displacement from the mean. Now we can write acceleration to be the second derivative of displacement is equal to minus k times x. K is generally referred to as the spring constant. This is the force required for unit displacement. Now we write x double dot, that is the second derivative of displacement, is equal to minus k divided by m times x. Call this as equation 1, call this as equation 2. Solution of this equation is x equal to a sine omega t or x equal to a cosine omega t. This we name as 3, this we name as 4, where the constant omega is the angular velocity. If you take the second derivative of the solution, the first derivative is a omega cosine omega t. If we have taken the solution to be 3, and the second derivative is minus a omega squared sine omega t. So this is minus omega squared into x. Now we can compare equation 5 with equation 2, and we find that omega squared equal to k divide m, or omega equal to k divide m square root. Since omega is equal to 2 pi by t, we can find the time period. Therefore, what is the trick to find the time period of an oscillator? The trick is to write the equation of motion in the form 2, that is to find the acceleration of the system under the restoring force. Put the constant that appears with the displacement is equal to omega squared, from where time period can be obtained. Now we apply the trick to find the time period on a system that is as shown in the figure. There is a beaker which contains some amount of water, and I have a test tube which I have filled with a little bit of sand, and the test tube can float vertically in the water. Now if I push the test tube against the buoyancy, force of buoyancy, and release it, then this is going to execute simple harmonic motion. The question is, what is the time period of this simple harmonic motion? Now in order to solve this problem, let us imagine at an instant of time the test tube is x below its normal position, its mean position. So we can find the force of buoyancy on the test tube. Force of buoyancy will be equal to the weight of water that it has displaced. So this is equal to volume of water multiply by density of water multiply by the acceleration due to gravity g. So this will be equal to area of cross section of the test tube multiply by the displacement multiply by density multiply by g. So this we write as pi r square, where r is the radius of the test tube, into rho into g into x. So this is the force of buoyancy. This we can write as, which is the restoring force. So this we can write as equal to minus mass of the test tube with its content multiply by d2x over dt squared. So if I write mass of the test tube with its content equal to m into d2x over dt squared should be is equal to pi r square rho g times x. So we obtain acceleration equal to minus pi r square rho g divide m times x. Therefore we can write the angular acceleration omega to be equal to square root of pi r square rho g divided by m. For some systems we cannot write the equation of motion as given in 1 or equation 2. For such system there is another trick. We know that at the extremities, that is at the maximum displacement, the energy of the oscillator is fully potential, and at the mean, that is at zero displacement, the energy is fully kinetic. We can equate these two energies, that is we can write kinetic energy at mean equal to potential energy at the end. We can find the velocity at the mean from kinetic energy, and that velocity would be the maximum velocity. Now as x is equal to a sine omega t, velocity x dot is equal to a into omega into cosine omega t. Now the maximum value of velocity would be equal to a times omega. That will happen when omega into t equal to 0. That is, it is passing through the mean. So if we can find V maximum from this equation, that is equation 7, then we can find omega from equation 8. So this is another way of finding omega, and if we know omega we can find the time period. Now let us have a system this is a pulley and we have a mass m which hangs by a thread, and the other end of the thread is attached to the rim of the pulley. The pulley is massless or having a negligible mass, and it is also frictionless. Now for such a system, to find the time period by using equation 1 would be difficult. So we try the second trick. Now at the position A, when the mass is released from the position A, it goes down and then it goes to the other side and it oscillates. Now at the position A, the whole energy of the system is potential, and therefore maximum potential energy is equal to m into g times r, where r is the radius of the pulley. And when it comes down, when the mass comes down such that it is over here, then the whole energy is kinetic energy, So we can put this equal to half mv square maximum, because for the situation B, the velocity of mass m would be maximum. So from here we can write V maximum equal to twice g times r square root. Now we know that velocity maximum would be equal to r times omega, because r is the amplitude of the motion. So this should be equal to square root 2g times r. Therefore omega will be equal to square root 2g divide r. From where we can find the time period, because omega is equal to 2 pi by t. So 2 pi by t is equal to 2g over r. So t will be 2 pi into square root r divided by 2g. Now we can verify this equation dimensionally, because for g the dimension happens to be L into t to the power minus 2, and for r it is L. So square root of that would give me t, so which is the time period. So dimensionally this equation is correct, and this is the way that we can find the time period of an oscillating system by using the second method. Now thank you for watching, and if you have any questions you can contact me. My email address is Dr. Atish Mazumdar @gmail.com, or you can give me a friend request on my Facebook account, which is Dr. Atish Mazumdar. Thank you.